For most of our history, if we couldn't touch it, see it, or climb it, we couldn't study it. Our knowledge of the Earth was defined by the reach of our physical senses. That biological limit blinded us to the systems shaping the Earth's surface and atmosphere. Deep tectonic plates grinding miles below us, global atmospheric currents, and glaciers moving fractions of an inch per year all happen on scales that escape direct human observation. Scientists could build mathematical models to explain these invisible forces, but without a physical way to test those ideas in the environment, a theoretical model remains a set of unverified equations. This creates a mandatory partnership between the researchers who theorize about the Earth and the engineers who build the equipment to measure it. Major leaps in Earth science arrive alongside new machinery, engineered tools designed specifically to give the planet a physical checkup. We cannot manage what we cannot measure. Bridging our sensory blind spots with technology provides the high-resolution data needed to track planetary shifts that are otherwise invisible. This drive to measure the unseeable creates a specific rhythm of discovery. A researcher builds a theoretical model, pushes it as far as the math will go, and eventually hits a barrier. At this data wall, the scientists know exactly what information they need to prove their concept, but they lack the physical sensory capability to record it. This diagram outlines the innovation feedback loop. A theoretical limitation creates an engineering prompt, triggering a new tool. These tools act as extended senses, capturing previously impossible raw measurements. The data flows back, either proving the idea or forcing a revised theory, requiring better tools. Inside this continuous loop, theoretical knowledge and practical engineering are interdependent. Neither discipline progresses without the input of the other. Take the early efforts to map the inside of the Earth. Researchers knew the planet wasn't a solid, uniform rock, but they couldn't drill deep enough to check the internal structure. They hypothesized that the Earth had distinct internal layers, but because they were locked at the surface, they were unable to verify the geology beneath them. The engineering response was the invention of advanced seismometers. These instruments were built to detect the specific frequencies of energy waves traveling through the Earth's crust after an earthquake. As these advanced sensors were deployed across the globe, they fed raw wave data back to the labs. They recorded the speed and refraction angles of vibrations moving through the planet. By tracking how those waves bent and slowed down at specific depths, that data turned a hypothesis into a measurable fact. It proved the boundaries of the crust, mantle, and core. Discovering these internal layers immediately prompted harder questions about how heat and pressure transferred between them, causing the feedback loop to grow more complex with each new discovery. Today, we have moved beyond isolated historical observations. We are monitoring the vital signs of the entire planet in real time from orbit. The environmental and geological pressures we face today are immense, but because of our measurement tools, we can quantify these shifts with increasing precision. This global map tracks data from planetary systems. By applying the feedback loop of science and technology, we convert environmental changes into actionable prompts for researchers and engineers. Shifts in regional climates, the depletion of freshwater aquifers, and strain along major fault lines are now actively being quantified by this global sensory network. These instruments act as an artificial extension of human senses, allowing us to monitor the environment at a scale our biology never intended. The evolving symbiosis between human ingenuity and scientific measurement provides the data necessary to navigate environmental changes and manage the resources we depend on.